last time we had an introduction to the Brayton cycle, and the Brayton cycle is used to understand or model stationary gas power plants where you burn natural gas. And this is an image of a GE plant or gas turbine. You bring the air in, compress it, then expand it through the turbine. It's all connected with a shaft, and this is where you would connect up a generator to make electricity. If the utility needs to build a new power plant to bring more capacity online, they're building natural gas. That's what they're building, a lot. They've been building a lot last 5 to 10 years. Okay? And they're also going to do a combined cycle plant. It typically won't be strictly, some of them are strictly natural gas, but if the high efficiency are going to be combined cycle plants. So today we're going to talk about the regeneration, reheat, and intercooling. Have you ever heard of regeneration? Yes, we did in the vapor power cycle. How about reheat? Yes, we did. And the same motivation that we introduced them and they use them in the vapor power cycle is the same for gas power. But there's no intercooling for a vapor power cycle. It's for a gas power cycle. Just as a review, we had the air standard Brayton cycle, a number of assumptions. I prefer that we get good at solving problems assuming constant specific heats. And we had a compressor, flow through the compressor. The burner is modeled as a heat exchanger. Then we go through the turbine. And in the physical system, there is no extra component out here. This is exhaust gas. It goes out the flue. We do have a physical compressor. We do have a physical combustor. We do have a physical turbine, but we don't have a physical fourth component. But that's introduced to make it a cycle. Without that, it wouldn't be a cycle. The working fluid needs to go in loop. That's a cycle. Okay? So then it's cooled in heat rejection, and then back to 1 again. So we can plot it on a temperature entropy diagram, a TS diagram. From 1 to 2, here it's shown as isentropic. 2 to 3, constant pressure heat addition. 3 to 4, expansion through that turbine, isentropic expansion. And then 4 back to 1, pressure is equal to a constant heat rejection. What's it look like on a PV, pressure volume diagram? Well, you have a very steep curve. That's S equal to a constant isentropic compression. Then you have constant pressure heat addition to 3. And then you have isentropic, S equal to a constant, expansion in the turbine back to 4. And then 4 to 1, what do you have? Constant pressure heat rejection in that heat exchanger. All good? So this is what it looks like for that problem that we solved last time, plotted with real data, okay? Where I have to arbitrarily introduce the entropy. So I set state 1 has an entropy of 1 right here. And then it was around 300 Kelvin. We went through a compressor with a pressure ratio, I think it was 9, and it boosted the temperature up to around 600. If you had some irreversibilities, it could even be higher to get it up to this high pressure line of 810, I think it was 810, right? kPa. And this line was what pressure? 90 kPa and a pressure ratio of 9, I believe. All right. And then you go through from state 2 to state 3. What are you doing? You're burning. The temperature's going way up, a combustion. And then from 3 to 4, first you go 4S, just like you did 2S, and then 4 actual, having some isentropic efficiency for that turbine. So that's for the problem we solved last time. Physical numbers plotted. Also, you can do it for the pressure volume diagram. Here it's a little harder to distinguish, but these are the same characteristics. So we have isentropic compression to 810 kilopascal. The temperature goes up. It's not shown on a PV diagram, but the temperature was, what, 600? And then if you have some irreversibilities, this is the same data plotted, okay? What you have is a higher specific volume at the end, because of the higher exit temperature for the same pressure. So V2 is going to be greater than V2S. Okay? And then you have constant pressure heat addition, followed by isentropic expansion, the solid line. If you have the irreversibilities, you have the dashed line, and it goes to the low pressure, but now it's much higher specific volume because the temperature at 4 is higher than the temperature at 4S if you had isentropic expansion. Does all that make sense? Good. Please, hopefully, study and read. Ready for a clicker question? Let's go ahead and start it. So, if the compressor isentropic efficiency goes down, if it decreases, in your mind, start with the 100% isentropic efficiency, then go to 90%, then go to 80%. See, the isentropic efficiency of the compressor is going down. Okay, if it goes down, how does S2 change? How does the entropy at the exit S2 change? Does it increase? Does it decrease? Or does it remain unchanged? And show the results. And so a lot of people said, look, if the efficiency goes down, there are more irreversibilities, the exit entropy goes up. True? Very good. Let's go to the next question. So if the compressor isentropic efficiency goes down, the efficiency of the compressor is going to go down. Think about 190, 80, 60. What does T2 do? The temperature at the exit of the compressor. What does T2 do? Everybody in? Oh, we'll shut it down in 60 seconds. All right, let's take a look. Well, okay. What do you think that exit temperature does? Goes up. Look back, I think this diagram right here. What did the temperature do because of increasing irreversibilities? It went up. Okay, very good. If the compressor isentropic efficiency goes down, if it decreases, this is the same thing, same direction. The isentropic efficiency of the compressor goes down. How does W of C change? What is WC? That's the work going in to the compressor, right? The work going into the compressor. This is a positive value. Don't worry about negative. It's a positive work into the compressor per unit mass. Units of kilojoules per kilogram. So I'll turn on the clicker and we'll give you 30 seconds to answer that one. How does WC change? 5 seconds. And we show the results. All right. What's if I do a first law, is this H2 minus H1? Yes or no? And is that for constant specific heat, T2 minus T1? And we just said, hey, the exit temperature is going up as the efficiency goes down. Hence, the work needed to drive that compressor goes up. That's right. That's right. So you could work out that T2 actual is equal to T1 plus, what is it, T2S minus T1 divided by the efficiency of the compressor. Is that what you're thinking? Right? So what's the correct answer? A? Yes. Okay. Now let's talk about the regenerative Brayton cycle. That word regenerator, we introduced it when we had vapor power. What was the idea behind the regenerative Rankine cycle? To preheat the liquid before it went into the boiler. So it was a feed water heater. And so the same idea, you take a look at a temperature entropy diagram. Where are you heating? Where are you heating the fluid? Well, you're heating the fluid from state 2 to state 3, true? So it's good to bring in heat at high temperature. It's bad to bring in heat into the working fluid at low temperature. Just a good rule of thumb. It's shown by entropy. Where are you rejecting heat out of the working fluid? From 4 to 1. Well, when you reject heat, you want to reject it at low temperature. You don't want to reject heat to the ambient environment at high temperature. Wasteful. So they say, you know what, you're rejecting it at really some high temperature, and you're adding, you know what, let's just draw this straight across. It looks like T4 is greater than T2. So if we could somehow get this heat transferred over, we wouldn't throw it out to the environment, we would put it into the cycle where it's useful. Same idea. So we take the turbine right here and we reroute. Take it out of the turbine, come back and put it into a heat exchanger, then continue on. So in this heat exchanger, you're trying to take that hot working fluid, the exhaust products, and use it to heat up the fluid that's coming into the combustor before it gets to the combustor, because this is where you're buying that expensive fuel to combust to make things hot in the combustor. True? Okay, that's the idea. So here is a sketch of that regenerative heat exchanger called a regenerator. It's sitting right here. So 2 is what comes out of the compressor, and then we introduce, the book introduces, the new state X. There's something different about the label for this state than all the other states that we've been using so far in the textbook. What's the difference? X is a letter. X is not a number. And so right when you thought you had the pattern down, you got to be careful here, okay? So X is a letter signifying a state. It's after the regenerator, before the combustor. Well, likewise, the first time you see X, you may think, what do you think if you saw X before this plot or this time? Quality, right. And now you also have, after the turbine, 4, and it exits the regenerator at Y. Y is a letter. First time you might see Y, you're just studied vapor power cycles, you may think mass fraction that went back to feed the open or closed feed water heater, right? So we have to recycle our terms. So X and Y mean different things. They're now states. So what you do is you want the temperature at X to be as high as possible. Could the temperature at X ever be greater than the temperature at 4, the exit temperature out of the turbine? That's not reasonable. It's just a heat exchanger. So 4 can get really close to the temperature at X. I'm sorry, the temperature at X can get really close to the temperature at 4, but it can't exceed it. All right? Likewise, if I have 1 kilogram going this way, what do I have? 1 kilogram going that way, right? So we have the same mass flow rates. And so that's what the book introduces. It's efficiency or effectiveness of the regenerator, not based on temperature, but based on enthalpy. You have a question?
Yes, I think it says that the temperature of X cannot be greater than the temperature of 4.
That's right. This is the temperature at 4. This is the temperature at X, is slightly below. See, the temperature at X is slightly below the temperature at 4.
Yeah, you have it the other way.
It cannot be that, right. Temperature X must be less than, thank you, I see what you're saying. It must be less than the temperature at 4. Thank you. Okay. So in terms of, we have to have now a measure of the effectiveness or efficiency or whatever of this heat exchanger. So the effectiveness is the term used in this textbook. And they're saying, look at H4 minus H2. That's the maximum change in enthalpy that's possible. What is the actual change in enthalpy? Well, it went from 2 to X, HX minus H2. That ratio is going to be less than 100%. When it's 100%, I have a perfect heat exchanger. Its effectiveness would be 100%. So that's the definition of the regenerator effectiveness. If you assume constant specific heats, Tx minus T2, C sub P, T4 minus T2. Cancel those C sub P's, and now you have it in terms of temperatures. Okay. Reheat. We've seen this strategy for improving the efficiency of the vapor power cycle. When you talked about reheat, what did you want to do? Pass it through part of a turbine, take it back for more heat added in the boiler or steam generator, then go back through another turbine stage. Same idea here. So you'll have two combustors and two turbines. So this is the high pressure turbine, this is a low pressure turbine, and it goes back for some added heat because you're going to bring in this heat, let's say from X to 3, you're bringing in all of this heat at relatively high temperature. When you expand it partially to an intermediate pressure, the pressure of this second combustor, put right here, this is P high, this is the pressure of the second combustor, this is the pressure low, okay? Then you could bring in some more heat to go from A up to B, from state A to state B in that second combustor. Bring in heat into the working fluid at high temperatures, great for performance. Reject heat at low temperatures, great for performance, okay? So this is a strategy for improving the efficiency of the Brayton cycle. Make sense? Let's take a look at another one. Intercooling. You were already exposed to regenerative, Rankine, and also the Rankine cycle with reheat. Both of those concepts were also used in the vapor power cycle. But there's nothing to compare in the vapor power cycle with intercooling. Or is there? Well, I guess there is one thing, but it's not direct. So the idea is to reduce the amount of work that's required to boost the pressure of the gas. All right? So if you look at the Brayton cycle, the back work ratio typically is very, very high. What was it? The work to run the compressor divided by the work of the turbine. So not only do you want to maximize the turbine power or work out, you want to minimize the work to drive the compressor. That's the idea behind intercooling. How can you minimize that work? Well, here's the strategy. Take the compressor and bust it into stages. First stage, second stage. In between, put it to a heat exchanger called an intercooler. You know the temperature of 1 to C, right, this state C, the temperature at C is going to be greater than the temperature 1. Why is it hot? Because you're beating it up in the compressor. You're squeezing and pushing it. You're doing a lot of work. It's compressible, the temperature goes up. Cool it down. Reject some heat to the environment. Try to get the temperature at D down to as low as the temperature at 1. If you can do that, then when you continue to do the rest of this compression, it'll cost less net work. Instead of having just one compressor, 2 stages with the intercooler. Okay? How does that look like on a TS diagram? Well, let's not put in any inefficiencies of the compressor. Let's say they're isentropic. So we go 1 straight up to state C, and then we stop at this pressure. This is the pressure of the intercooler. And we don't go all the way up. That's where you would be if you went all the way up to state 2 without the intercooler. That's how high a temperature it would be. But what you do is you cool it off. Here I'm showing the cooling back down to the same temperature. So the temperature at D would be back down to the temperature at 1, and then finish the compression going up to this high pressure line. So you can see that the temperature to exit is lower than the temperature 2 if you would have just had one compressor stage. Okay. So some people have seen the word intercooler used before. Where have you seen the word intercooler used before? In automobiles, in engines, as well as in diesel, big semi-engines and stuff. Typically associated when you have a turbocharger or a supercharger. True? So if you have a turbocharger, you often have an intercooler. So what do is you put the intake air through the turbocharger. It boosts the pressure. That's the purpose of the turbocharger. But because it boosts the pressure, it's now hot. High pressure is good. Hot is not good. So you try to cool it back down at high pressure and then feed that into the engine. You can pack more oxygen into that displacement volume of that internal combustion engine. And hence you could stuff more fuel in there, get more bang, get more power. That's why turbocharged engines work that way. But they work a lot better with the intercooler. Okay? So cool it down so you can pack more oxygen into the cylinder. Same with the supercharger. Instead of having it driven by the exhaust gas, the supercharger's taking mechanical energy off the crank to boost the pressure. All right. Here's another clicker question. So, what is the name of a device that is used to increase, that's a key word, increase the pressure of liquid water? I have a black box. Here's water in, here's water out. Here's water at state 1, here's the water out at state 2. What is the name of the device that is typically used to call, what do you call it, that boosts the pressure of liquid water? Ready to stop? Here it goes. This is the easiest one. That was very close. It's a pump. Okay, I don't know what to say, but we have a beautiful section 4 or chapter 4 of this textbook where they try to do a good job of what is a heat exchanger, what's its purpose, what is a turbine, what's its purpose, what's a compressor, what's its purpose, what's a pump, what's its purpose, and distinguish it between that and a compressor. They use the term pump when it's negligible change in volume of the fluid flowing through it, but your purpose of the pump is to boost the pressure. What's the purpose of a compressor? To boost the pressure. But it's a fluid that typically gets compressed in the process. That's why they call it a compressor. I'm not trying to be tricky. All right. What is the minimum work needed to increase the pressure of water? The water comes into this box called a pump at 100 kPa and 25 degrees C, and I want it to go out at 1100 kPa. What is the work needed? This is the minimum work needed in units of kilojoules per kilogram. Everybody understand the question? I'm only going to give you 45 seconds. You may need to do a little doodling on a piece of paper. Maybe you need a calculator, but you only got 45 seconds. This is the work that goes in. I'm not worried. I know it's into the pump. The pump requires a shaft to drive it, to make it work. Per kilogram of liquid water that goes through it, how many kilojoules of energy supplied in that shaft to drive the pump? 1, 30, 100, 300, or 1,000? Well, what do you think? Is there a consensus in the class or not? There's not. All right. How do we make this calculation? Well, it's a minimum work. What does that keyword trigger? Internally reversible flow through that pump. And we just finished water. We just finished pumps. We said VDP, 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 right? And so the minimum work is the specific volume of the incompressible liquid that doesn't change between inlet and outlet. So V1 is equal to V2. And the dP is the change in the pressure. Well, this is a low blow, but I know the density of water, about 1,000 kilograms per meter cube, but I can't remember the specific volume of water. 10 to the negative 3, 1 over 1,000. So it's 0.001 meters cubed per kilogram. Professor, I didn't have time to look that up. Some things you should just try to remember, right? Now, what's the change in the pressure? Well, you went from 1,100 to 100. It's 1,000 kPa. So we have a meter cubed times a kilopascal is What's the product of a kilopascal times a meter cubed? Kilojoule. So what's the answer? What is the final or exit temperature of the water? This was P2, right? What is T2? T2. Is it 25C, 125C, 225C, 325C, or 425C? I will stop, but I will only give you 30 seconds. All right, we're in. All right, I need to stop it. So let's go ahead and show it. Where are we at? 63 is correct. Remember my image on the, I showed on a TS diagram, and I emphasize when you have liquid water, you pressurize it, the change in temperature is minuscule. Half a degree, a third of a degree, 2/3 of a degree C, maybe 1 degree C. Unless you really, really boost it, okay? What device is used to increase the pressure of air? Do you call that a nozzle, a compressor, a heat exchanger, pump, or boiler? What is the name of the device that intakes air, and the purpose of it is to boost the pressure of air? Get a pencil and paper, a calculator for the next question, please, okay? So if you need to get it. All right, everybody's in. We stop, we show the result. It's a compressor. Are some people just playing with me? I mean, I don't want to embarrass anybody, but I'm not certain people are giving it their best shot at times. Okay, let's continue on. This one you'll need to do a little scratch work to get the right answer. Okay? What is the minimum work needed to increase the pressure of air, not water, from, guess what, the same temperature and pressure that was inlet to the same exit pressure that we just analyzed for air? For water. Didn't we just analyze it for water? So I have a box. This box, I don't call a pump, I call a compressor. But I'm bringing in air, and I'm bringing in it at 25 degrees C and 100 kPa, and I want it to go out at 1100 kPa. What is the work, the minimum work to drive that device known as a compressor? I will turn it on, and we only have so much time to solve this problem. Try and do it from your memory if you can, with a little work with a calculator and a pencil, 2 lines or 3 lines. All right, we're stopped. Let's go ahead and stop. And we show the results. And here are the results. They're all over the map. True? All right. If I do a first law analysis for this problem, okay, if I do a first law analysis, is the work to drive the compressor, is it H exit minus H inlet? Is it the change in the enthalpy? Yes? Do you agree? I like constant specific heats. It's air. It's an ideal gas. I really want you to bone up on constant specific heats. Why? Because you can do back-of-the-envelope calculations so quickly, right? So is this C sub P T2 minus T1? Yes. All right. This is the hard part. What is roughly the specific heat of air? C sub P. 1.005 or something like that. About 1. Okay, so ballpark, look at, this is ballpark, right? Okay, so we're looking at 1.005. You can forget the 005. Kilojoules per kilogram Kelvin. Got it? Now, I need to find T2, but I already know what T1 is. This is the inlet temperature T1. I can either put 25 or 298. I'm going to put 298. That's a big hint for how I'm going to get T2. I need to get that exit temperature, T2. Some people solved this problem correctly. Some people did. I can look. There's an answer. A was selected, B was selected, C was selected, D was selected, and E was selected. True? Air, minimum work, through a compressor. Give me an equation to get T2. T1, P2 over P1. How many people have seen an equation like that? I know I asked you to get your calculator because you needed it on this one, okay? So, can you run your calculator and tell me, everybody that has one right now, tell me what T2 is? 592. We have an answer of 592. We'll see if other people confirm it or not. I want you to run it. I want you to run it, you 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 run it. What's K? 1.4. At room temperature. K is 1.4, room temperature. Did you agree? I got a confirmation there. I'm looking for a couple more confirmations. You confirm it. You're 3, 4, 5, 6, 7. Excellent. 8, 9. I'll stop at 10. 10. All right. So that's it. So now somebody run the work. Take that 290. It's 300. D. Isn't it D? All right. Look at this. Do you understand everything that's on this slide? Do you understand everything that's on this slide? Good? Think. Ready for next question? An adiabatic and reversible air compressor has an inlet of 100 kilopascal and 25 degrees C. I've seen that before. And an exit pressure of 1100 kilopascal. What is the exit temperature of the air? And I turn on the clicker response, and we'll give you 60 seconds. And we're done. And we show the results. That's the results, right? But, oh, they required it in degree C. What do you get? 319. Well, what's the best answer? True? All right. Let me ask you this. If I put my hand on the pipe, the water pump pipe, it's exiting the water coming out of that pipe. Am I going to burn my hand on the water pump pipe exiting the pump? No, I'm not. I put my hand on the pipe coming out of the air compressor, immediately right after the air compressor. Am I going to burn my hand? Yeah, you are, right? Big difference. Same pressure difference. All right. So that shows you how much energy is required to boost the pressure on the compressor. If you wanted to, you could take a look at a pressure volume diagram, and visually what you do is, remember we were taking it up the whole way to go from this low pressure to high pressure. If you take it up to some intermediate pressure, right, and then cool it off at constant pressure, it'll kick over, and then continue the compression. The visual image of the work per unit mass is not the area under the curve on a PV diagram for an open system. It's the area to the left of the curve. It's this area over here. And so this is the work per unit mass with one big fell compressor without any stopping and then cooling. And this is the work if you stop and cool. So what is this area right in here a visual image of? The reduction in the work per unit mass. True? True. Take a look at the end of chapter 6. So if you now if you include isentropic efficiencies in the system, then you start to have to kick over for the compressor, kick over for the compressor, kick over for the turbine, and there's multi-steps in solving the problem. But I think you can do it. If you could just analyze one compressor with the efficiency, isentropic efficiency, then you can analyze two of them. It's the same process. Likewise for the turbine. True? True. I think we're done for the day.